After the Second World War, physicists and the U.S. Navy shared a sudden, urgent obsession. They needed to push radar technology into higher frequencies. They needed the space between these wave peaks to shrink. The scientific motivation was obvious. As you move from centimeter wavelengths down into the millimeter and submillimeter range, you hit a jackpot of molecular data. At these shorter lengths, the number of distinct molecular lines multiplies, and their ability to absorb energy spikes. But to generate these high frequencies, you need extremely small oscillators. Traditional electronic hardware was simply too bulky, reliably maxing out at longer centimeter-length waves. At Columbia University, physicist Charles Townes spent years trying to manually shrink these components. He formed a Navy committee and toured laboratories across the United States and Europe looking for a mechanical solution. No one had a single viable idea. The hardware approach had reached its absolute physical limit. To get shorter waves, physicists were going to have to leave traditional electronic components behind entirely. Townes realized that nature had already built the perfect microscopic hardware. Atoms and molecules were naturally small enough to act as the high-frequency oscillators the Navy wanted. There was just one massive hurdle. To extract a respectable, usable amount of light power from a collection of molecules, you have to excite a huge number of them at once. Under the normal rules of thermodynamics, that requires applying extreme heat. By the time you reach the temperatures needed to generate that power, as the temperature climbs here, the molecule vibrates so violently that the chemical bonds simply snap apart. The heat destroys the very oscillator you are trying to use. Because of the strict laws of thermal equilibrium, using a molecule to generate short waves looked scientifically impossible. In April 1951, Townes found himself sitting on a bench in Washington, D.C.'s Franklin Park. He had woken up early, running this exact temperature paradox over and over in his head. Then he caught a flaw in the basic assumption. The destructive heat limit only applied if the molecules were resting in thermal equilibrium, the standard state where temperature is balanced across a system. If you could force a collection of excited molecules into a state of complete non-equilibrium, that thermal limit vanishes. There would be no ceiling on their potential radiation intensity. Townes pulled an envelope from his pocket and started running the math. He hypothesized a molecular beam method using ammonia. By passing the ammonia through a filter, he could physically separate the highly excited molecules, isolating a pure high-energy stream. Routing that pure stream into a resonant cavity tuned to the exact emission wavelength would corral the emitted energy, forcing it to amplify. The numbers on the back of his envelope held up. You could bypass the temperature limit and create powerful, controlled microwaves. Back at Columbia University, Townes teamed up with student Jim Gordon and postdoc Herbert Zeiger to build the device. But translating that math into reality was agonizing. After 2 grueling years of manual labor in this lab, they still hadn't achieved a single oscillation. The lack of progress attracted the attention of the department brass. 2 esteemed chairmen, including predecessor Isidore Isaac Rabi, both future Nobel laureates, marched into Townes's office. They told him the physics wouldn't work, he was wasting departmental money, and he had to stop. But Townes was an associate professor with tenure. The department could express their doubts, but they couldn't fire him over a theoretical disagreement. So he looked at 2 of the most respected minds in physics and flatly refused to shut the project down. 2 months later, Townes was lecturing in a classroom when Jim Gordon dashed through the door. The device was finally working. The entire class abandoned the lecture to witness the demonstration. Townes and Gordon successfully built the first maser, Microwave Amplification by Stimulated Emission of Radiation. The breakthrough only survived because a structural academic protection allowed one physicist to stubbornly defy the institutional consensus. The maser mastered the centimeter wavelengths, but Townes immediately set his sights on the original goal, pushing this non-equilibrium physics down into the submillimeter and visible light spectrums. By 1957, he was discussing the idea with Arthur Schawlow at Bell Labs. They faced a serious mechanical hurdle. If you used the maser's standard enclosed metal cavity to capture highly energetic optical light, it would bounce erratically, creating chaotic, multiple-mode oscillations. Schawlow proposed a brilliant modification. He suggested abandoning the enclosed box entirely and using 2 parallel mirrors, a Fabry-Perot resonator, to precisely reflect and amplify the light beam. Swapping the metal box for a set of mirrors provided the exact control needed to turn a theoretical optical maser into a workable design. Townes and Schawlow published their mirror resonator concept in 1958. Almost overnight, it triggered a frantic industry-wide race dedicated to building the physical device, what we now call the laser. The initial success of the maser had proven to the industrial sector that molecular oscillators held immense practical value. The ensuing laser technology went on to dictate the direction of modern engineering, driving advancements in everything from global telecommunications to precise surgical medicine. By interrogating a basic assumption about thermodynamics on a quiet morning in a public park, Townes managed to break through a physical engineering wall and conjure the entire field of quantum electronics into existence.